Let's do a quick video about mechanics because we have an exam tomorrow. This whole exam is really going to be about like Lagrangians and stuff. So we should know the Lagrangian is just going to be L equals this kinetic energy minus the potential energy. And usually we just go straight into doing Euler-Lagrange equations. So we have this base, which would be say d of dx or maybe d dt. And then, like you see here, this is the base, it's t. And then we have our two like other coordinates, which are going to be the velocity and the position. And so, we take the velocity derivative here, and then we take the position derivative here, and we get our Euler-Lagrange equation. And it's important to realize that these derivatives basically give us momentum and force. So this is kind of the most important part here. We're trying to figure out what momentums are, what forces are, what's conserved. So, for example, um, we have the central force here that would be like U, R, T. And notice how it depends on R, the radius. And so, therefore, because it depends on the radius, it conserves angular momentum. It doesn't depend on theta. So that means that theta is kind of this ignorable coordinate, and um, and so it's conserved. We kind of go down here, for example, if x was the ignorable coordinate, what it would mean is that if you're trying to take the Lagrangian here, notice how this particular Lagrangian doesn't have an x in it. It doesn't depend on x, it depends on y and y prime. We're even doing like an integral over dx, but this does not contain x. And so we can call x the base. We could try taking the derivative, but because the derivative of the Lagrangian in terms of x is 0, that means that 0 goes on the right side of the equation here, right, for the Euler-Lagrange. And so the partial derivative for the velocity segment here is going to be equal to 0. And so that means that it has to be a constant, like this term right here. In order for the derivative to be 0, that term has to be a constant. And so then we get this situation where the momentum in the x direction is conserved, it's constant. So that's cool. Um, and that's wonderful. Let's try now looking maybe at this example of a bichristochrome cycloid. So we have like the potential up here, and something might fall along sort of a. We're trying to figure out what the fastest path is here, minimize the time, and so it's going to fall in this sort of a weird way to here, and we're going to get some kinetic energy at some point. So we can go through the derivatives here, and we sort of did this in another video, but eventually we have to use the Beltrami identity. The Beltrami identity is the idea that if we have an ignorable coordinate x, then we use the Lagrangian minus the velocity times the derivative for the velocity here, set that equal to a constant, and that's what we did here. So you can see we could quickly solve something like this and get an equation of motion. The equation of motion are called the extremals, and we get something like this. Oh, really, we get this equation here. And so we can see how like the equation of motion becomes like a cycloid. So it's cool. This is just kind of a simple way to apply the Lagrangian in a situation. Um, what else can we do here? So this is interesting. So like here's an interesting thing. Basically, a lot of these setups have symmetries. And sometimes if you choose the correct coordinate system, then you can pull the symmetry out of the equations. But if you don't use the right coordinate system, then it could just hide the symmetries. So it's important to do this with the correct coordinate system. Another thing we had to do maybe was like check out equilibriums. Um, so that was difficult. Let's focus on this like constraint issue because I was just working with this. How the constraints can break symmetries. Constraints, for example, there's actually two ways to set them up. So either you modify the Lagrangian equation and then you just use the regular Euler-Lagrange equation to figure out everything. This is a way that you can actually pull the constraint force out if you just take the partials in terms of the lambda. So the multiplier here, that's the Lagrange multiplier. So either you modify the Lagrangian and then you take just a regular Euler-Lagrange to find the equations of motion, or you can take the original Lagrangian, t minus v, and then modify the Euler-Lagrange equation itself, which is maybe a little bit better, and then you can figure out what's happening. But let's note that the constraint forces is equal to this lambda df over dx, kind of like this. So we have to figure out what the constraint force is. A constraint force, for example, in a pendulum would be the tension, because the tension is holding this thing in constraint. And then there's this other external force, which is the gravity force, which is the applied force. So you can kind of work with that. But it turns out that the total forces is going to be equal to the applied force plus the constraint forces. And then we use this D'Alembert's principle by saying that constraint forces do no virtual work, meaning they're perpendicular to the motion. That makes sense here. Notice that the motion would be kind of like this, and the constraint force is perpendicular. That's why it does no work. And you try to solve the equation, Newton's equation, like this: F equals ma, and then you sort of plug in that you're taking a variation in terms of the of dr here, or dt. I'm not really too sure. This is like really complicated, but it ends up that because the constraint force does not work, then you kind of get only the applied forces remain, and then this somehow is able to derive the Lagrangian and stuff for you, which the Euler-Lagrange equations. So that's kind of difficult, but this is just the general idea: is that you've got applied forces and constraint forces, and the constraint does not work. So so that's interesting. Yeah, let's look at these conservative forces. So we have, three ways. As soon as you know a force is conservative, you know three things about it. First, you can find the F from the negative of the potential, negative gradient of the potential. You can also do a little integral around dr here, a little circular loop, and the work is equal to 0. You can also find the cross product. This is the curl. If the curl is 0, and this is basically what that means. So there's a lot of things you get from just knowing that a force is conservative. Just give me a moment. I think something froze. Something froze. But hopefully nothing more broke there. Um, Here's another important thing to know about the action. If we're going from here to there, we're finding this little variation around the path, and we have these vanishing fixed endpoints where we're doing this variation on position, and these initial points and these final points equal 0, which makes sense because that means you're starting and ending at the exact point, but along the path you might have some variation, and this is how we sort of take the variation for the action. Yes, the Euler-Lagrange is great because it can solve weird integrals. We've already kind of, like, here's a weird integral we can solve with it. Um, and holonomic versus non-holonomic, it's just basically whether you have positions where you can use a coordinate system to do something. And let's consider now an Atwood machine, for example. It's better if we use something like maybe x on this side, and then this is like L minus x, because you have the length right here, which is L. So if we have x on this side, we can subtract x on the other side. And this is how you basically just beat all the Atwood machines. You just set up a coordinate system like that, and that's pretty easy. Now, here's another interesting thing is that if we have a rotating pendulum like this, where it's literally spinning around, it's spinning around like rotating like this. Not necessarily just side to side like a pendulum would be, but also spinning in terms of this, uh, actually makes more sense if that is the theta going that way. Just realize that, like, that's an angle like that, but there's also W equals the 2 pi version, because you can spin this around. This is only going to go from here to there, this theta. But if you try to spin this around 360 degrees, that's a different angle. That's 0 to 2 pi. That is the azimuthal spin. And so instead of the polar spin, this is like kind of like, I don't know, it's hard to show this in 3D, but essentially you get a little circle like this with your pendulum here. So that's how it can go around in a circle like that. If it does, at equilibrium, then the radius is fixed. So this is important. Okay, quite interesting. There's just some machines that we can work on. Path integrals is C right there. And probably the last thing we need to take a look at is the velocities, maybe here in Cartesian, spherical, and cylindrical. And when we do that, we get these different Lagrangians in those coordinate systems. And yeah, so that's pretty much it for what we need to know in terms of this stuff. Although there is one more section that might be helpful for this exam, and that's just remembering that we have damped oscillators. So the plus version of the oscillating formula is the simple harmonic motion, which leads us to sines and cosines. And if we have the minus version, then that means that the exponentials are not imaginary exponentials, but they're just growth and decay exponentials. And I suppose you can put it in terms of cosine, but just the cosine, like there's no sine version there, I guess. And if we go into the overdamped version, you can see you actually have two real exponents. So that's kind of like this one over here. If we have the critical version, then we have two equal alphas. And so then we have just the actual W naught is the resonant frequency. So these are solutions to overdamped, critical, and then underdamped. Over here you have two complex alphas. And here's the solution to that one. This one starts to get a little bit crazy. You can also reduce to this form right here. And I think there's also a driven oscillator somewhere. But for the driven, here's the driven oscillator. Uh, the driven oscillator requires solving a particular solution, and then you get something like this for the particular solution. You have the amplitude here being the response. These are just some formulas that might help if we are given these types of formulas on the exam. So that's pretty much it for this mechanics review. Hopefully that was helpful, and